Hello and welcome to MT3. We are still on the topic of linear operators. This is Hobson Bence 8.2, but now we're going to look at some examples of linear operators. I've introduced you to the algebra. We have seen how you can write a linear operator A hat in its matrix form, but how is it actually done? So before we go on, let's just go over the notes from last time. A hat takes us from a vector space V into a prime space. We could have a dimension change. The dimension of the original space is n. The dimension of the new space could be m, where m is typically less than or equal to n. And the basis of the original space is the EI hat basis. And the basis of the new space is the FI hat basis. All right. One of the key equations here was how does the operator A hat operate on the basis vectors of the space we start from. And we introduced this idea here that the operator A hat operates on the basis vector of the V space. It transforms it into a vector in the V prime space, which must be represented in terms of the F basis. And these coefficients here must depend both on I, because I is not a dummy index, it's on the left hand side, so it must be on the right hand side, and it should depend on J, because we are summing over the coefficients of these basis vectors of this space. Okay, and this is an important equation. Now the order here does matter. I have written it as AJI. It does matter for self-consistency. You could just as well do everything I'm doing here with the order the other way around. You will get a different ordering to all your equations, the indices in your equations, but as long as you're self-consistent, you will be correct. However, if you want to follow Riley's book, then you will use this ordering. So A operating on EI is equal to the sum over J, A JI F hat J. All right. Now the very first example I'm going to be talking you through is the identity operator. The identity operator takes a vector from the V space and keeps it the same. So I hat operates on X and you get X back. That means our space doesn't change. So V prime is in fact equal to V. The dimension doesn't change. M is equal to N. And the basis set stays the same. So the F hat basis is the same as the E hat basis. Okay, so our key equation, which I've written down here again, it becomes, you just replace M by N and the F by E because of this. All right, so now let's have a look at how the operator the I hat, the identity operator, operates on the basis vector E hat I. But it gives us E hat I back, because that's the definition of the identity operator. Using the sum, this must be equal to the sum j goes from 1 to n of I, j, I, E hat j. And what this means then is that if we write it down, let me put that down here. This would be I, 1I, E1 plus I, 2I, E2, and this goes on. At some point you will have j equal to I, in which case you will get a term which looks like this: I, E hat I, and then it will go on all the way to the last term, which is going to be when j is equal to n, so I, N, I, E, N. Now if you compare this term here with this sum on this side, you will see that we must have the matrix components I, J, I is equal to 1 when I is equal to j. That's this term here. And all the other terms should vanish because they are not on this side, which means that when I is not equal to j, we should have a 0. Now that's the Kronecker delta, which we've seen before. And in matrix form, what this translates into pictorially is that the matrix I, which is the matrix representation of the identity operator script I hat, that matrix is diagonal with 1s on the diagonal when I is equal to j, when row is equal to column, and zeros elsewhere. Or we can write it more compactly as this 1s on the diagonal and zeros elsewhere. This is the identity matrix. And that's the very first operator in matrix form that we will see. So let's take a special case just to convince ourselves that this is the right thing. When n is equal to 2, the identity matrix will be the 2 by 2 matrix 1 0 0 1. If I take any vector x, it's a column vector x1 x2. If I operate with I on x, I should get x back. Let's see. So I operates on x. We have the identity matrix times the column vector, and I do the usual matrix vector multiplication, and I get back x. So this is correct. All right. So this is the identity matrix is the matrix representation of the identity operator. The next example I'm going to be looking at is that of the rotation operator. Let me just pause it. Right. So the next example is the rotation operator, and we'll denote this by script r hat. Now, if you're working in a two-dimensional space in this example I'm going to be showing you here, then the rotation operator takes your basis vectors and rotates them by an angle theta in the counterclockwise direction. So e hat 1 becomes e hat 1 prime, and e hat 2 becomes e hat 2 prime. Now, this operator does not change the dimension of the space. It keeps it, the vector space V remains V, its dimension remains the same, and the basis set needed to span the space remains the same. Alright, that's good. Now let's look at simple, before we go any further, what's the simple relationship between these these rotated vectors and the original ones? Well, here we have to go back to basic trigonometry, and if you haven't seen this before, please just work it out. The vector e hat 1 prime can be written in terms of the basis set e1 and e2 hat through the trigonometric relation. Well, basic trigonometry gives you e hat 1 prime is the cosine theta e1 hat plus sine theta e2 hat, and e2 hat prime is equal to the minus sine theta e1 hat plus cosine theta e2 hat. Now, I remember that I should have a cosine on the diagonal, because when theta goes to 0, e1 prime hat should be equal to e1, and e2 prime hat should be equal to e2. Alright, so you do need, if you're unsure of exactly where the sines and cosines go or what signs they have, then you need to do work of your trigonometry. Alright, good. Now let's have a look at our key equation. So our key equation says that r hat operates on a basis vector, the e hat I, and it gives us something which is a linear combination of the basis vectors of the new space. But, you know, this is the same space. So j goes from 1 to m, where m is 2, r j I, and these fj's are in fact the same as the e hat ij's. I'm sorry it's a bit cramped over here, but I hope you can see it. Now take the case I is 1. If I is 1, then we have r hat operates on e1. Remember, that gives us r hat operates on e1 hat, and it gives us e1 prime hat, which is given by this expression here. So I've written it down here. R hat operates on e1 hat, and that gives us e1 prime hat. And from this expansion here, which is rather too cramped, let me just comma, yeah. From this sum over here, we can write this as, remember, I is equal to 1, so we have r11, this is not f, r11 e1 hat plus r21 e2 hat. Okay, now let's compare it with what we've got here. So compare this is, remember, it's equal to e1 prime. Compare it to what we have there. And this lets us define, so let's have a look. This is our 1 1, and this is our 2 1. let's do the case where I is 2. So now we have R operates on E2, that gives us E2 prime, and over here we have I is 2, so we'll have R12 E1 hat plus R22 E2 hat. Now that should be equal to E2 prime, which is here. So compare this and this with that. And what we see then is that this first term here is R12 and this second term is R22. So now we have all the terms in the R matrix. The R matrix, which is the 2 by 2 matrix, it's 2 by 2 matrix because the original space had dimension 2 and the final space also has dimension 2. This matrix has the form R11, R12, R21, R22, and from here, let's get that back, R11 is cos theta, R12 is minus sine theta, so let's put that down, cos theta minus sine theta, and R21 is sine theta, R22 is cos theta. There we are. Okay, so now we have the R matrix. Now what this means then, and I'm going back up the lecture notes now to this equation here where we use the matrix form of the operator to relate the components of the vector x with those of the vector y. So what this means then is if we have, therefore, if y is equal to the rotation operator operating on x, then yi is equal to the sum j goes from 1 to 2 r, I'm going to leave this blank here and then let's put an x j there. Let's remind ourselves what the order of those indices should be. Yj is equal to a ji xi, sum over I. Now I wrote it as yi, so I'm going to have to just swap the i's and j's. So yi is equal to y rij xj, and we can now write this nicely for any vector and any component, or if you wanted to write it in its matrix form, y1 y2 is equal to cos theta minus sine theta cos theta multiplied by x1 x2. So we now can relate the components of any vector x with the vector y and through this rotation matrix. So this rotation matrix takes the components of x and transforms them into the components of y. Okay? And that's the second example. Now you will see more examples in your homework set, so we'll discuss the remainder in the tutorial sessions. Thanks for watching.